Welcome to next lecture. We will continue our discussion on co-channel interference. Okay, so this will be our model for this co-channel interference. So we will have a hexagonal cell of radius r, radius of hexagonal cell, and as you know, d is the distance between centers of nearest co-channels. Okay. Now we also know this d by r ratio, we derived it yesterday. It is equal to root over 3n, where n is taking value I square plus ij plus j square. Okay, this is given as separate symbol q, and it is called channel reuse ratio. Channel reuse ratio. Okay. As an example, if you take I is equal to 1, j is equal to 1, so your cluster size n is 3, your ratio q, that is root of 3 into 3, which is 3. Okay. Similarly, if I is equal to 1, j is equal to 2, this n is 7, and this will be root of 21, which is 4.58. Similarly, if you chose I is equal to 2, j is equal to 2, it will be 12. So this is under root of 3 into 12, which is 36, which is roots 36, 6. If you chose I is equal to 1, j is equal to 3, this is 13, this is root over 3 into 13, which comes to be 6.24. The impact of this q will be seen when we will derive the some necessary relations in interference, and then we will see what is its impact on the interference. Right now, let me denote by I naught as number of co-channel interfering cells. Okay, so actually I naught is the total number of cells which are using same frequencies, and hence they are interfering with each other. Also, let us denote by S the signal, and let's denote by I the interference. Okay, then we have this S over I, which is also called signal to interference ratio. Interference ratio. Okay, SIR for short, or SPI. Now let me give you an example. Suppose this is your cell, and suppose these are the co-cells, co-channels. That is, all of these use same frequency. There are in between other hexagonal cells also, but they use different frequencies, so there is no co-channel interference between them. There is only, so if you are, so I will represent this by A, this is also A, these are all A's. Okay, they are all using same frequencies. So if a mobile user is here, right, and this other mobile user here, other one here, other one here, so they may interfere with each other, right? So let's say this interference is I1, this interference is I2, this interference is I3, this is I4, this is I5, this is I6. So total interference will be the summation of this, right? And 6 is the I0. I0 is equal to 6 here. I am just showing it example. There are 6 co-channels here. So S by I can be then written as S is the signal which is received by a mobile divided by summation I is equal to 1 to I0. Okay, notation is a little bit bad. I0 I don't prefer to use to denote a number anyways. So it means that interference from ith co-channel. S is the desired power signal from the desired base station, and I is the interference power caused by ith interference co-channel base station. Okay, so mind it that I is the power of interfering base station. See, the mobile signal will not reach. It is actually the base station signal which will reach. Okay, because mobile signal is very weak. Base station, has a very good power, so base station signal can reach. Now, I will here tell you one fact, but we are going to do that in good detail in large scale, fading models. That is about how the power decays, okay, with distance. Suppose you are here and your transmitter is here, okay, and it is emitting some signal at some average power level P0. Now at a distance, suppose D, what will be the power? Okay, so in general, power decays. So power at distance D, I will write like this. How it decays? It is proportional to P0 divided by D to the power n. Okay, where n is some exponent, is called path loss exponent. Okay, path loss exponent. So for free space, when there is no reflection, for free space, this is basically n is usually 2. So P of D, is proportional to P naught by D square. Okay. Sorry. Now, this is one relationship. We can basically write it in a very formal way, in this way. Suppose P naught is not the power at this point. We take some fixed distance D naught. Okay, so P naught is the power at distance, fixed distance D naught, and D is any variable distance, and P is the power at that. I will write here PR, that is the received power here. So we can easily write that PR, see, this P naught is also inversely proportional to D naught to the power n, and PR is also inversely proportional to the D to the power n. It decays with distance. That is the main thing. So I can easily write PR is equal to P naught D over D naught to the power minus n. Okay. We will go deep into this equation in large scale modeling. Right now you take it as this. So if I take 10 log to the base 10 on both the sides, I will get 10 log to the base 10 PR is equal to 10 log to the base 10 P naught minus 10n log of D over D naught. We prefer, because usually powers are having large value, we prefer logarithm. So this is a dB power, so I will write here PR in dB is equal to P naught in dB minus 10n log D over D naught. Okay, now coming back to this figure, see, these distances we represent it by D. Suppose this is D1 distance, this is D2, this is D3, this is D4, this is D5, this is D6. All the base stations, emit power of the same level, right? So now if you take up, suppose these two hexagons, suppose this is D1 distance, let the power here be P naught. So power at this base station, because of interfering base station, will be P naught, right? uh, D1 divided by some D naught, sorry, just a moment, yeah, D naught to the power minus, right? Similarly, because of another interfering base station, the power, if distance is D2, the power will be P naught D2 over D naught to the power minus n, right? And what if we take the extreme case, the radius of this is R. Now you take this hexagon, the radius is R. What is the extreme case? Extreme case is base station is here and a mobile user may be at the edge. Okay, this is the worst case where you will get the weakest signal. So we will take that worst case. So in that scenario, if this power is P naught, what is the power here? It will be P naught R divided by D naught to the power minus n, because it decays. Okay, so now what will be then the signal to interference ratio? So S over I will be equal to, so it is P naught R over D naught to the power minus n divided by summation P naught di divided by D naught minus n, right? I is equal to 1 to I naught. So this D naught is constant, fixed. P naught is also fixed. So we will get R to the power minus n divided by summation di to the power minus n. I is equal to 1 to I naught. Okay. Now if we assume that, and which is mostly true, if all interfering base stations are equidistant from the desired base station, and that D1 is equal to D2, suppose equal to D. Okay, and that's also called, we only take first layer interference. First layer means this: suppose this is the base station and these are the equidistant base stations, which are the base stations. There may be second layer base stations also. Yeah, sorry for interfering. There may be second layer here, but their signal will be weak because they are more far away, so we will discard them. We will only take the first layer interfering base stations. That is why we can assume that the distance is same. Now if we take the distance to be same, so what will it become? So S over I will become R to the power n divided by I naught D. So you are basically summing it up I naught times, so it will be R to the power n divided by I naught times D to the power n. It's actually minus n, yeah, sorry. So which can be written as D to the power n divided by I naught R to the power n, which is D by R to the power n divided by I naught. This actually is Q, or D by R is also equal to root 3n to the power n divided by n. See, what we want, signal to interference ratio, we want to be as large as possible, because that will make us that signal should be large or interference should be less. So S by I ratio should be as large as possible. And we see that S by I is proportional to n to the power n by 2. So as cluster size increases, okay, this is the cluster size, we get more and more signal to interference noise. This also demands us that we should choose large number of clusters. That is, we should choose large number of cells which will use different frequencies. Okay, we take a very typical example which is most common in especially 2G and 3G systems, which is the cluster of size 7, n is equal to 7. Okay, so we can denote that something like this. So here is the base station in which you are assuming the communication, where you are computing the S by I ratio. This is another base station. Okay, okay, now this distance is R. Okay, suppose you are here, you are considering this signal to interference ratio here, and from this point, now let's look at this carefully. So we are considering this center point to this distance. This is D, right? But look at this distance. It will be D plus R, okay, because this R part is extra here. Okay, and rather look at this distance. I'm not able to draw it properly. Actually, the circle I have drawn ellipse. So this will be D minus R. This also will be D minus R. Center, so this will be again D, and this will be D plus R. They are approximate, but still, little bit accurate. Now, in this analysis, we are not considering. So we are taking the mobile to be at the edge. Okay, so this is the worst case scenario, and the distances are not equal here. If R is much smaller than D, then definitely you can assume to be equal. So this is a little bit exact analysis. So then what will be S by I ratio for this? Right? So you have the formula. So R to the power minus n, right? Divided by summation I is equal to 1 to, now what is here I naught? It is basically 6, right? I naught is 6, so di to the power minus n. Okay, so R to the power minus n will remain as it is. And what is di? Now di is d minus R 2 times. You see, this and this is d minus R. Similarly, for 2 hexagonal cells it is 2d. For other 2 it is 2 into, oh sorry, there is minus n here, d plus R, right? Now we will again study this in large scale fading, that for various ground reflection cases n is equal to 4. Okay, so I can write as over I as R to the power minus 4 divided by 2 times d minus R minus 4 plus d plus R minus 4 plus d minus 4. Okay, we can divide numerator and denominator by R to the power minus 4. We will get 1 over 2 times, I can write here d over R minus 1 plus d over R plus 1 plus d over r minus 4. I have just divided this r to the power minus 4. So I can also write it as 2 times 1 over 2 times q minus 1 to the power minus 4 plus q plus 1 to the power minus 4 plus 2 times 2 is outside, so plus q to the power minus 4. That is the significance of reuse ratio. You can see that again, to increase s by I, we need this q reuse ratio to be as high as possible. So in next part of lecture, I will show you how these computations are important in designing a cellular system, in even choosing how many hexagonal cells or base stations should be packed up in one cluster.